Hello, so this question is the third question of this year's BMO round 2, and it is considered as the hardest problem in the paper. So let's just take a look at this question. It looks very accessible from the start. Well, the problem statement is simple. We have a 30 by 30 grid, and we have 300 ones, 300 zeros, and 300 minus ones to fill in the 900 gaps. And the question is asking us whether it's possible that the 60th row and column sums are all different. Well, in my opinion, the hardest bit of this problem is that it seems like there are multiple ways to get going, but in the end, it turns out that the solution is pretty narrow. So there is only one way that will lead to this solution. I've tried many other methods, but in the end, either they're too messy to show, or they just come down to the same constraint. Another reason why this problem looks difficult is that it seems that it is possible to do that. So it really is a subjective question because you kind of have to guess the answer before you start working on it. I mean, I could imagine in the heat of an exam, if you guessed that it is possible that the 60 rows and columns, they have all different sums, then it will be quite hard to turn your head around. One good way is to think about, well, can I reduce it to small numbers, for example, if it's a 3 by 3 grid? Small numbers is also a good thing to try, but overall we need to tackle the problem because it is quite a specific number, so it's usually hard to generalize. I'll try not to be subjective in my process of working, and I will clarify when you kind of have to make a guess. But first of all, as a BMO2 candidate, you have to get to the conclusion that, well, if we have 300 ones, 300 zeros, and 300 minus ones filling up in these rows and columns, then the maximum number you can obtain is 30, and the minimum number you can obtain is minus 30. That is fairly obvious because you have 30 ones and 30 minus ones. That will just give you the two extremes. And realistically, you can obtain any single value, integer values obviously, between 30 and minus 30, and that actually gives you 61 numbers. Now, you need 60 different numbers, and it will be quite intuitive to guess that 0 is the odd one out. And it's actually very simple to check, because if we sum up all the values here, well, we know the total sum must be 300 times 1 plus 300 times 0 plus 300 times minus 1, which is just going to give you 0. So if we have row sum, let's just call, row sum, R1, R2, and R30, and let's call column sums C1, C2, and C30. So if we sum up C and R, well, that should give us 0 as well, because, these two numbers should be equal. And we also know that if we want 60 different numbers, then they have to be picked from these 61 numbers. So the odd one out has to be 0, because say if we take minus 1 out, then the sum will not be 0. It will be minus 1 instead. So now the problem is reduced to, well, we have numbers 1, 2 to 30 and minus 1, minus 2. Can we fill up the numbers 1, 0, and minus 1 in such a way that somehow the row and the column sums have these exactly 60 numbers? Now, it is time where you have to take an intuitive guess. And the answer is no. Well, the only way I can see that you can kind of turn your head around if you unfortunately guess that it is possible is that you try to work things out and you realize it's not possible. I mean, it really depends on how far you go, but one thing you may consider if you guess it's possible is that, say, we need I don't know, without loss of generality, let's say we have a row sum of 30, then we need 31s. Now we know that there can't be a column sum of minus 30 because, well, at some point, the -1 and the ones will intersect at one cell, and that cell could not be both 1 and -1. So we know that there has to be some kind of imbalance, whereas in order for it is possible to have 60 row and column sums to be different, you kind of want a bit of symmetry inside. So maybe that is a hint that it's not going to be possible to have different values. But we have to prove it somehow. And the way we do it, well, there aren't many information we can do. So perhaps we could try, well, considering we summed up these values, a good way to think about is if we sum up the absolute values. Well, if we sum up the absolute values, then quickly we can work out the value should be 1 plus 2 plus 30 plus the absolute value of -1 plus -2 plus -3 plus to minus 30, which will just be the same as that. So it will be 30 times 30 plus 1, 31, which is 930. Now, is that really obtainable? Now, this number is only attainable when some kind of perfect symmetry exists. But we have shown using the previous contradiction that the perfect symmetry doesn't exist. So we kind of have to bound it somehow. And the way we do it is we utilize that imbalance. Let's suppose there are n columns of positive sums. Well, we can make a quick table. Well, if we have n columns of positive sums, then we immediately know that the number of positive sums of rows is going to be 30 minus n. And similar with negative sums in columns, because there are 30 columns in total, so if there are n positives, then the rest are negative, so it's 30 minus n. And similarly, we can quickly fill out this table. The last value is n. Well, how are we going to use this information? So let's suppose that at an arbitrary row and column, there has to be an intersection cell, and let's say the cell is 1. Well, let's just consider how this cell will contribute to the expression. Well, let's just assign this, let's call this S. Well, how is this cell going to affect S? Well, we can see 1 is a positive number. So if both the row column and the row sum and the column sum are positive, then this one is going to have a double contribution effect. So it's going to do a +2. Otherwise, it could do a -2 if they're all negatives. But it depends because, well, if it's 0, then if you do a -2, it will actually give you a +2 effect on the absolute value. Or if you have, let's say, 4 and then you do a -2, it will give you a -2 effect. And if you're 1, then it will give you no effect. So it all depends on what's going to happen when -2 joins the negative columns. But what we can guarantee is that the maximum contribution that one singular cell can make is +2. And that is only possible when its sign is the same as its corresponding row sign and column sign. That's a very optimal solution. And similarly, if we have -1 and we have negative rows and columns, then, well, we're going to do -2 to the overall sum. But remember, this is, we've taken the modulus, so it's still a +2 effect. And this is really the abstract part. Once this part is done, then it really is fine, because now we can do an upper bound estimation of S. Well, here we are trying to think very optimally. Let us assume that, well, we can see for the positive ones, the number of intersection of positive columns and positive rows is going to be n times 30 minus n. And let's just assume that all the intersections will give us a +2 contribution. That is obviously a very, very, a very optimal estimation, but this just gives us the upper bound. And similarly with the negatives, let's just assume we can arrange them in such a way that they're all going to give us negative modulus effect. So let's just label that. Well, the total contribution will be, 2n. In fact, it's 2 times 2n times 30 minus n. And that is 4 times n times 30 minus n. Now, it's very, it's very clear that we can use an AMGM inequality here. If we just let, n is a and 30 minus n is b. We know a plus b over 2 is always bigger than or equal to square root of ab. Well, here we essentially have a square root of it. So let's do, it's going to be a plus b whole thing squared is going to be bigger than or equal to 4ab. And so the maximum value for ab is going to be a plus b squared over 4. So we can see that a plus b is 30 here. So the maximum value for their product would be 900 divided by 4. And if we substitute back into the original expression, 4 times 900 over 4 is 900. So the maximum value that S can obtain is 900. But previously we've just concluded that S is 930. It's just contradiction. So we've proven that it's not possible to have 60 different row sum and column sums. Well, let me just make it clear. I just want to investigate a bit more on, is it true for all grids? Well, I've previously stated that you can use small examples. Is the logic same for 3 times 3 grid? And is it possible for all grids of multiple 3? Well, let's find out. And that's actually just an extension. So I'm just going to mark a boundary line here. Let's do it 3 times 3 grid. Well, we can actually use the same trick. Well, here the corresponding will be 3 1s, 3 0s, and 3 minus 1s. And, we could get, it's going to be -3, -2, -1, and then 3, 2, 1. So the corresponding S for the 3 by 3 would be 6 times 2, which is 12. And we could do the same. So it will be S upper would be 4 times n 3 minus n, where the maximum equals 3 squared over 4 times 4, which is 9. So 9 is smaller than 12 contradiction. And if we generalize to n squared, then, well, the x exact value would be half times 2 times n plus 1, which would be n squared plus n. And s upper would just be n squared over 4 times 4, which is n squared. So the difference between the optimal maximum and the exact value of s would always be the side length of the grid, which is kind of like a bonus from the question, because the question doesn't really ask you to do that. But I just thought it's a fun result to derive. And we can see here, well, in the 3x3 example, 12 minus 9 is 3. That is the difference between the exact value and the theoretical estimation, which is the side length of the grid. And similarly with our previous question, well, if our actual value is 930 and our theoretical maximum is 900, then the difference is 30, which is also the side length of this grid. So I thought it's just a fun result. Overall, I think this question is tricky, mainly because there is a very limited way of doing it, and it kind of is tricky. I mean, it took me a while to work out the way to use absolute values to give bounds, which is really not a normal technique in the limit style problems, and it is the official solution. So comment down below what you think. If you have a different solution, or you think your solution is more elegant, please do leave a comment, and please like and subscribe. Thank you.